Hi everyone, thanks for having me here this year as well. Today we're going to talk about some underrated gems about WebAssembly and peculiar aspects that you might find in your Rust development process when developing for the web and targeting JavaScript runtimes that will run your WebAssembly. So I'm Alberto Schiabel, I come from Venice, North Italy, and you can find me online at jcomino. But before I finish introducing myself, you may want to scan that QR code so that you can save the slides and code examples for later. So I've been a software engineer for around 8 years. I mostly work with Rust, TypeScript, and Node.js ecosystem for backend development. And I'm one of the open source maintainers of Prisma, a type-safe data access tool for databases. We're trying to make it easier for folks to get started using databases and provide observability for that. And also I'm a contributor to the open source full-text search database called Orama. And again, it's the same stack, Rust, TypeScript, and we work at the edge with WebAssembly tooling. I also provide workshops and consulting, so feel free to reach out. First of all, how many of you were at EuroRust last year in Berlin? Let me see your hands. OK, quite a few of you. I see some familiar faces and also a lot of new ones. Well, perhaps those of you who were there last year will remember that we talked about some issues when dealing with data serialization, like sharing data types between Rust and TypeScript with WebAssembly. And while it's kind of easier and intriguing to work and try to make these two languages, Rust and TypeScript, work together, that's not enough for production use cases. We need a bit more. But before getting to that, let's start with a baseline. What is WebAssembly? Well, you can imagine, think of it as a very fast bytecode that's kind of designed to offer near native speed for the web. And it runs on a virtual machine. And it's like a very simple virtual machine, so it has very few instructions. It's made to be very fast to start up and to consume low memory. Oops, sorry. It provides a virtual instruction set, and the caveat is that you don't have access to system calls. You don't have access to I/O, so you can't really interact with your environment, technically. But for our use case, that's just another portable compilation target for your cargo script. So whenever you build, you can just define the target as wasm-42 unknown unknown, which means it's independent of the operating system and CPU architecture you're going to run the WebAssembly code on, and just be done with that. You compile it once, and you run it everywhere. And for Rust and Node.js / other JavaScript runtimes / TypeScript integration, there is this fantastic tool called wasm-bindgen, which is maintained by the official community. You just need to install it. It's both a CLI and crate, and then you need to mark the public functions of your Rust libraries that you want to expose to JavaScript runtimes via the wasm-bindgen macro. And if you haven't done that before, imagine you have this simple example. You have your crate, demo-lib. Initially, you just have a library and the cargo toml. Once you build that crate, a new target folder is going to appear, right? And if you dig deep enough, you're going to find a .wasm file. What's that? That's the bytecode that corresponds to the result of your compilation process. But JavaScript developers, they don't want to deal with that, and also they do not know how to use the functions that are defined within that WebAssembly file. So what do they need? They need bindings. They need JavaScript modules that they can work with. And that's where wasm-bindgen comes to the rescue. It provides function definitions. It provides type signatures also. And it allows you to integrate with the JavaScript object and types. All right, now that we have this kind of baseline knowledge set up, it's time to see some peculiar aspects of WebAssembly. In particular, how do we deal with error management, and how is that different from the standard Rust error management? First, let's take a look at errors. We usually we model for failure in Rust by functions that return a result type. And a result type is just an enum variant. It can either represent a successful result or a failure via the error constructor. And those functions usually can be retried, so they are safe to retry. And probably the easiest example you're going to see is a divide function. So notice the signature. We take a bunch of numbers, we divide them, and we return a result, which is possibly a number in the successful case, or a string telling us where we messed up. We conditionally fail if we're trying to divide by 0, otherwise we just divide. And how do we deal with that? Where we can either pattern match, or we can use the question mark operator. And how does that translate to JavaScript and TypeScript? Well, you see that in the signature of the function, we don't really have any equivalent to our result. So we just return value. The OK constructor is translated as is. In case of failure, we actually throw errors, and we have the try-catch mechanism that you're probably familiar with from other C-style languages. The JavaScript developers, they expect to have an error object in the catch clause, and that's going to be a bit important later. Why? Because they provide us an interface, of course. And how would the Rust function that results in a failure and is translated to WebAssembly look like? For a small example, let's consider a JSON parsing utility. We're going to use the asserted JSON, and we're going to take a string, and we're going to try to convert that into some sort of internal struct. And in case of failure, we just print what was the error message. So we return a result of the structure in the successful case and a string in the error case. What's the problem? The problem is that the error case isn't necessarily translated in an error object in JavaScript. And if you deal with any standard library for JavaScript that needs to do with error management, they are going to result in runtime errors. And what's the problem? The problem is, in this case, in the catch clause, we're going to get a string. We take a look at the type of at runtime, it's going to be a string. And you don't want that for developer experience. So what you want to do is actually to provide an error. And thankfully, wasm-bindgen provides that JS error top-level type value that you can use. You can just derive from it, or you can use the from trait. And in fact, if you try to run that in JavaScript, you're going to see you're going to get an error. Its name is always, property is always going to be error. And you're going to get a nice message telling you what the problem was. For instance, you were missing a field in the JSON string you were trying to parse. And the cool part is that you can also have your own custom errors. As long as you derive from the error trait and the display trait, you're not going to need JS error. But then the most tricky part is, how do we deal with panics? Well, panics, they model unrecoverable errors. It means that you ended up in a state where there is no safe way of getting around it. So most you can do is just log the error some way, maybe send it to your dashboard system, and restart the application and hope for the best. What's the problem with Rust and WebAssembly? Well, the stacktrace you're going to see is not going to be it's not going to be useful. Why is that? Because the error message where it usually tells you the error message, which you will expect to see the coordinates of where your error arises in the first place and the file, the Rust file that generated that error, you're not going to get any of that. You're going to get just unreachable as a string. And then a bunch of hexadecimal strings in the error stack. You can't really do much with it. And what's the problem? Also, you can't unwind your panics. Because when targeting WebAssembly, you can only abort. That's the limitation currently. And a peculiar thing is that whenever we trigger an error, for instance, by invoking the panic macro or by calling the unwrap method on a function that will return a result, what happens is we get an error object always, and its name is always going to be runtime error. So we start to see at least a way of differentiating at runtime between WebAssembly errors and WebAssembly panics. But we see the message is always going to be unreachable, and we want to fix that. And how can we retrieve such a panic info with WASM when running that in JavaScript? Well, it turns out that if you look at the wasm-bindgen documentation, all they're going to say is, well, you can use this crate, and the crate is going to print the panic info to your console.error. And how can it access that? Well, it turns out from WebAssembly, you can use external C blocks. You can refer to global objects in the JavaScript namespace, and console, which is the equivalent of printf, is there. What's the catch? You will lose all those panic infos. Like, you will print them, but you wouldn't retain them. You wouldn't be able to ship them to your login system, and so on. So I was not happy with that. And also, this crate uses one thing we're going to also use, which is the STD panic set hook. So even though it's true that in WebAssembly we can't unwind panic stack, we can still apply set hooks. So you can define a function that runs immediately before your process gets aborted. So what's the idea? The idea is that you could, just like you could have a global console to send the panic info to, you could potentially have a global panic registry, right? Just a class, a TypeScript class that offers a get and a set interface that you can access at any time in JavaScript. And how would it look like from the Rust point of view? Well, first of all, we will need to define an external C block. And we can tell wasm-bindgen, hey, provide me an alias. We're going to call it set wasm-panicinfo. That's going to be a function. And that function is going to be a one-to-one match to the wasm-panic registry variable defined in the global namespace for JavaScript. And we're going to call the setPanicInfo method on it, which accepts a string and doesn't return anything. And how do we configure the panic hook? Well, we just use std panic hook. We define a function as the first argument, and we're going to have access to the panic info. We turn the panic info into a string, and that's going to be our message that we want to print on the errors we capture on the JavaScript side. And from before, we observed that the name property of the error we see in the catch clauses in TypeScript is always going to contain a name called runtime error. So we can provide a TypeScript function that just tells you, hey, return true whenever you find a wasm panic, and return false whenever you have a normal wasm error. So we can distinguish the cases in which we can recover the computation, or we just need to fail the process. And if we try to run that, as long as we remember to set up the panic hook, and you need to do that either manually, or you will need to run it once with a one-cell crate, you just trigger the panic, you take a look at the catch clause, you're going to see, hey, you actually get a panic. So in order to retrieve the panic info you wanted so desperately, you can just refer to that wasm-panic registry. You're always going to find some entry there, right? If you end up in that case. And you can see there are messages panicked at the name of the file, the line, and the column. And it also tells you what was the cause. In that case, we also get the same error message. The same string we pass to the trigger panic method, because in there we just call the panic macro. Is it going? All right. What about asynchronous functions? Right? What if, so far we've only seen synchronous functions exposed to the WebAssembly bindings and used in JavaScript. But asynchronous functions are boring. Asynchronous are a bit more fun. They usually are also a bit more useful. And in Rust, also the previous talk mentioned this point. Those are modeled with futures. You kind of need an external executor to run them, because otherwise Rust doesn't know how to deal with the top-level asynchronous functions. And these futures, they are lazily executed. You have this async await syntax sugar. How does that translate to the JavaScript model? Well, in there, when you're going to try to run WebAssembly bindings that are asynchronous, you have to await in there also. But the model is a bit different. So first of all, you don't have futures. You have functions that return promises. A promise is just a value that eventually is going to result into a value, or it's going to reject, and it's going to tell you the error cause for that problem. And they are eager. So as soon as you call the function, the promise is going to run under the hood. And if you don't await on it, you're going to leak the result. So you're not going to be able to observe the final result. And also, the CPU model is a bit different in JavaScript because it's inherently single-threaded. There are a few modern exceptions, but for our use cases, and also considering that multi-threading isn't really stable in WebAssembly, we're just going to consider single-threaded. JavaScript runtimes, they are quite fun. They have their own event loop, so you don't need an external executor like Tokio. And the fun thing is, did you know that you can actually run Tokio in WebAssembly? Turns out that you only need to not specify all the features it contains. So, for instance, you could use the read-write lock, which provides a locking mechanism with a future API. So you can await on stuff rather than just try to lock and panic if you can't lock. But the synchronous functions, without accessing I/O or like performing network requests right into a database, they're not interesting. Because why would we need that? If we want to await for, provide some delay, we can just use the setTimeout API in JavaScript. If we want to, we don't necessarily need locks because we are in a single-threaded environment. But we might want to programmatically run asynchronous functions defined in a WebAssembly context if we need to run on like constrained platforms. For instance, Cloudflare workers, they are pretty popular nowadays. Turns out that you can only define your code in JavaScript, or you can define that in Rust, and that gets converted to WebAssembly under the hood, which means you can't use crates that deal with system crates and deal with the native database interaction. Or you can just use JavaScript and take your Rust library, convert it to WebAssembly, load it from JavaScript, and use it from there. So you just write a minimal JavaScript layer, because we don't want to write JavaScript. And we write a lot of our logic in Rust, which is kind of what we are trying to do with Prisma. So from the beginning, we saw that WebAssembly technically doesn't really have I/O capabilities. It just doesn't have the instruction set for calling system calls. It just, usually you mostly use it for dealing with numbers, for dealing with like memory allocations, function definitions, but not anything that has to do with I/O. Turns out that this is a major limitation, so folks that are much smarter than me, they thought about a specification for introducing new capabilities, and they call that WASI, the WebAssembly System Interface. Technically, you could use that in the future to read files, perform networking, read from random sources of entropy, read from clocks, etc. What's the catch? It's still incomplete. It's still unstable. You can't use that, for instance, in the latest version of Node.js, which is the most popular JavaScript runtime, without experimental flags. And even though you want to try and use those experimental flags, you're not going to get network access. And also, they are not supported by many cloud platforms. So what's the catch? We need to find an alternative. And also, imagine this case. What if, for instance, you had a TypeScript ORM whose core logic is actually written in Rust, and currently you have a problem because you can't run on the edge due to the fact that on Cloudflare workers, for instance, you can't have FFI, you can't read files from the disk because you don't have access to the disk at all, and all you can do is just run WebAssembly. I'm just asking for a friend here. Well, turns out that we can revolve this logic around. So rather than using WebAssembly and using the WebAssembly instruction set to run I/O, we could just use JavaScript for what it does best, which is asynchronous I/O. And we can pass the control of these JavaScript functions to Rust code that is exposed via WebAssembly to JavaScript, so that we acquire ownership of those functions and we run them programmatically as we please. Can we do that? Yeah, it turns out that we can do that. So what's the idea? You first of all declare your JavaScript functions, right? Which are asynchronous usually. You define a higher order function in Rust so that it accepts a JavaScript function. And it turns out that you can use some crates like the JSSys crate to interpret whatever value you are given, whatever JavaScript value you are given as a JavaScript function, so you can have like call methods on it. And then you just delegate the responsibility of running those functions to the Rust code, so to the WebAssembly layer. And also, if you try to apply the wasm-bindgen macro to an asynchronous function in Rust, you're going to get a compilation error by default. you need to use the wasm-bindgen futures crate, which is also provided by the same Rust WASM organization, in order to achieve that. It's a little bit convoluted how it will work. I'm not going to spend too much on the details, but the idea is that you can have an asynchronous function definition in JavaScript. It's going to return a promise, right? So eventually it's going to resolve in a value, or it's going to end up in an error state. You can have a Rust function which accepts an asynchronous function written in JavaScript, and then some arguments. And then at some point in the future, it's going to call that function with said argument, and then maybe it's going to do something else with it. So we can imagine it could contact the database, it could perform a custom query. So for instance, in Prisma, we have our own SQL-like query language, which needs to be translated in actual SQL, and all of that is delegated to a Rust component. And we can imagine that then, from the Rust core, we want to run that. We want to connect to an external database, which is actually what I ended up doing for a demo we're going to see at the end. You need to go through a series of conversions. So from this JavaScript value you get to a JavaScript function, you want to call that, and eventually you're going to get a JavaScript promise. The promise is going to run under the hood. So eventually it's going to resolve. You need to convert it into a JavaScript future so that you can have access to the .await method. And once you get that, you get a potentially fallible result. But then you have your actual result of the computation. You can do a lot of things for that. Moreover, you can, like, if you don't want to deal with all this transformation every time you accept a function as an input, you can just define your own async trait. You can provide a simple definition. In this case, we're just using, we are exposing a method that calls one function with a single argument in an asynchronous way. The caveat is that you always have to provide like the self argument of the function. Since these are free functions, they are not bound to any object. You just press null, and that's it. And you just convert from JavaScript value to promise to future, and you wait, and you just return. OK, so what do I want to remember from this? So first of all, if you want to provide a decent developer experience for your JavaScript colleagues that are going to run your Rust code converted to WebAssembly, please ensure that your functions that may fail, please ensure that they end up in an error object. Because we've seen like plenty of runtime errors due to just trying to access the wrong thing with the wrong type. Moreover, if your WASM function panics, it's not safe at all to reuse any function from the same WebAssembly module. You need to restart your application and try again. But now you also can have access to the panic information, which previously you didn't. So you can save them to your like log storage. You can observe them and try to fix the bugs later. And hopefully that was something new that you learned today. Moreover, WebAssembly functions, they can be asynchronous. And actually, if you want to deal with I/O, which technically you couldn't, but the only alternative you have if you are in constrained scenarios such as running on Cloudflare workers is use that, you need them to be async, and you can just run them. However, if the architecture of your application allows to just write things either in pure Rust or in pure JavaScript, then potentially that's going to be the best way. Because still, WebAssembly is awesome, but transferring data back and forth between Rust and another language, you're always going to pay some cost in terms of CPU runtime. Technically, also in terms of memory allocation, but there are ways to get around that, and get in touch with me if you want to know how. But yeah, you ideally want to call WebAssembly functions as little as possible, and you want them to do as much as possible, so there are chances for the compiler to optimize rather than calling them every time. And I have a little, if you want to learn a bit more about WebAssembly, I have a workshop coming up in November at Rust Lab in Florence, if you're interested. But also, I have a little demo for you, because if you read the abstract of this talk, I mentioned a query engine that could run, could basically understand some input values, run some SQL from there, connect to a database. And technically, you can't do that with WebAssembly, but I'm going to show you that we can. So just to show you that I'm live, I'm here on, maybe I'm going to, OK. I'm on Cloudflare Workers. So a bit of the limitations, you only have 128 megabytes. You only have 10 milliseconds to execute your requests. You can only run JavaScript or WebAssembly. So you technically shouldn't have access to I/O. What happens here? This is a page where I can create. If I hit the create button, you should see, basically under the hood, I'm going to invoke a WebAssembly function. The WebAssembly function is going to take my JavaScript object input, it's going to transform that into a SQL query, it's going to insert, perform an insert statement on the D1, which is a SQLite database stored online on the Cloudflare CDN, and let's see how it goes. And the data is just random. And just to show you that, I'm not lying. By the way, you don't have any persistent state, so the only way that this could work is by persisting that in some other external storage. And the way it works, I'm going to just, we have an entry-level fetch request. At some point, we're going to get in touch with this method right here. Again. OK, router event, right. We have a get entry point. This is all TypeScript, but it executes WebAssembly. I am using a query engine, which I'm defining from a WASM module. Where does the WASM module come from? It's here. It comes from the WASM folder. And if we take a look at that, these are all bindings generated by wasm-bindgen. And what it does, it simply calls the query method, which is defined in Rust, exposed via WebAssembly to TypeScript. We pass an object. In this case, this is just an enum variant under the hood. In this case, we want to perform a selection, and we say, OK, select the data field from the event table, and we're going to just get the results, convert them with JSON, and show them with a very poor implementation of React.js. And then what can we do? Well, we can also post results. And how do we do that? We use a different query engine. This time we have this execute row function that actually runs the I/O, connects to the D1 database, to the SQLite database. All of this, you couldn't run it directly via WebAssembly instructions or like via pure Rust. You just run that, you call the query method, and you're golden. And if you're just interested in how it looks like, well, you just have, OK, these are all the trait definitions for calling functions in an easier way. We have an insert query, we have a selection query. Here we have the query input object, which is variadic. We can have different shapes. A query result, we're just going to have different shapes depending on whether you performed an insertion. You get the number of rows. A selection, you get the actual result set. And what's the class that we instantiated? It was called query engine. When you construct it and use the constructor macro from wasm-bindgen, you just take a JavaScript object. This comes from the JS_sys crate. You read the functions from it. In this case, I used the Doctor crate, but you could also just use JavaScript reflection, also provided by the JS's macro. And now I have access to the functions. And how can I call them? They are just JS function, so they don't really have concrete types for the input arguments and the output arguments. So you have to cast them in Rust and try, and hopefully you know what types they are referring to. You run the JavaScript here. By the way, you can also perform logging in WebAssembly as long as you set up the logging mechanism via crates such as wasm logger. And how do they work? They just have external blocks under the hood, external C blocks under the hood. They're gonna look at your global console, and that's kinda it. And you see here we have the panic handling mechanism. So in case of panics, we can call a global panic registry and be golden. And you have access to a repository where you also have a bunch of tests showcasing how I/O works, how async works, errors, and panics. So all the examples you saw before and much more in the repository that you find in github.com/jcomino/EuroRust-2023. All right, that's all. Thanks for having me, and it's been a blast. Thanks so much.